Good day to everyone. Today our group will discuss about a mathematical optimization problem. Before we start our presentation, please let us to introduce ourselves. My name is Liu Huitong.
My name is Proportion.
My name is Tan Ching Man.
My name is Chai Shui.
My name is Teo Hui Lin.
In this project, we aim to determine the most cost-effective dimension of the container while maintaining a fixed volume of 60 cubic meter. We will also calculate the minimum manufacturing cost based on the given material price. Furthermore, we will highlight the importance of this type of mathematical optimization in real-world application, particularly in industrial design, packaging, and manufacturing cost control. Let us begin by explaining the mathematical solution we use.
So the question is, a factory is designing a rectangular container as shown in figure below, with open top with the volume of 16 meter cube. The container will be used in the logistic and manufacturing industry for strong components. One side of the rectangular base, L, is required to be 4 meter long. The material for the base costs Rm8 per square meter, while the material for the side costs Rm2 per square meter. So basically, we are going to solve a problem to design a rectangular container with open top of fixed volume, and our main goal is to calculate the dimension of the container that minimize the total material cost. So in here, we can identify that there are several information that are provided, such as the container are rectangular shape, its volume is 16 meter cube, its base length is 4 meter long, its base cost is Rm8 per square meter, and its side cost is Rm2 per square meter. Then we will write all this information down so that we can clear what are the information provided that we can use for our calculation later. For the calculation part, first step, we're gonna calculate the volume of the rectangular box, which is length times height times width, L, H, W. We found this. Then since it's provided in the question that the volume is 16 meter cube, so L, H, W is equal to 16. And then we substitute this L equal to 4 into here. So by calculation, we can calculate the width in terms of H is width equal to 4 divided by H, and we mark this as 1. Okay, so after solving that part, the second part of calculation is to calculate the area so that we can find the total cost. Okay, for the base area is 4 times W, because 4 is the base length and W is the width. We don't need to multiply by 2 because it is an open top container. For the side, this WH plus WH is the lateral side. There are 2 lateral sides, so we plus 2 times. And this LH plus the LH is for the posterior and the anterior side of the container. And then we'll have got this 2WH plus 2LH. So since we got both base and side area, now we're gonna calculate the cost. For the base cost, we're gonna use 4WH to multiply by 8 because it is Rm8 per square meter, so we multiply 8. For the cost of the side, we use this one, the total side area, multiplied by 2 because it is Rm2 per square meter for the base cost. Then next, we will have this one, the total cost. The total cost is used the cost of base add by the cost of side, and we have this one. So we're gonna simplify it by substituting W in the form of H into it, and we'll calculate the height first. So now I'll pass it to Hui Lin to continue to find the height and the width.
Okay, so to find the value of H and W, we can first differentiate the equation for the total cost of the materials, and we will get negative 128h negative 2 and 0 and 16. And we will equal this equation into 0 because the derivative of the equation means that the cost is increasing or decreasing with the value of w. Okay, so by equaling the equation into 0, it means that the cost is stopped and it's not increasing or decreasing, and at this point it is at the minimum cost for the materials. So in order to find h, we can make the h as the subject by moving negative 128 over h squared to the left hand side and moving 128 to the right hand side, and we will get 8 as our value, and by moving the square to the right hand side we will get square root negative and positive 8. So after square rooting 8, we will get a negative value and a positive value. But since we are looking for the dimension for the container, we will not need the negative value, therefore the negative value is rejected. So we will get h as 2.828 meter. So in order to find w, we can sum it back into 1, which is w over 4 over h. So we will get 4 over 2828, and we will get the value 1.414 as the value of w. So we will get the value of h as 2.828 meter and w as 1.414 meter. So for the next question, we are required to calculate the minimum cost to manufacture the rectangular container. So from the previous question, we know that L equals to 4 meter, W equals to 1.414 meter, and H equals to 2.828 meter. And from the question, we know that the materials for the base cost Rm8 per square meter, and the materials for the sides cost Rm2 per square meter. So in order to find the minimum cost for the base, we can sub the values obtained just now into this formula, which is L times W, and we will get 5.656 meter squared as our minimum area. So in order to find our minimum cost, we can times this value with Rm8, and we will get Rm45.25 as the minimum cost for the base. And next, for the minimum cost for the side, we can sub the values into this formula, which is 2WH plus 2LH, and we will get 30.624 meters squared as our minimum area for the site. And in order to find the minimum cost, we can times that value with Rm2, and we will get Rm61.25 as our minimum cost for the site. So if we want to get the total minimum cost, we can just plus the minimum cost of the base with the minimum cost of the site, and we will get Rm106.50 as our total minimum cost.
Next, Sui, Huitong and I will explain briefly how this type of mathematical optimization is important in industrial design, packaging, or manufacturing cost control. I will talk about the industrial design aspect. First and foremost, the importance is eco-friendly and sustainable. Mathematical optimization ensures that the design uses exactly enough material to preserve the structural strength and durability. Therefore, the materials are used wisely and not overbuilt. This can avoid excess thickness that does not provide value to the container and may lead to material waste. As a result, the container can be lighter and environmentally friendly. Furthermore, the second importance is enhancing stability and safety. Optimization helps to make sure the container's height to its bottom width ratio is not excessive, which prevents tipping. For instance, the containers can be stored safely and are stable when stacking on the surfaces together, thus this minimizes damage to the container that might cause injury. Moreover, the importance includes improving practicality. It is because the containers will be designed so that workers can handle, move, and store it easily. For example, the workers can use forklifts to lift the container safely, as optimization helps designers select dimensions that are stable and compatible with mechanical handling. The user-friendly containers are easier to handle and clean up that fit in well with daily operations. It can assist workers to save time, which increases workflow efficiency. Last but not least, the importance includes in adaptability for various industry demands. Optimized containers can be designed to accommodate various warehouse layouts, transportation vehicles, and shelving systems. Since it is adaptable, the same container may be applied in many situations without redesigning. It also facilitates more effective processes and improved organization. Now I will pass to Sui to talk about the packaging aspect.
Now I'm going to talk about the importance in packaging. Firstly, the main importance is the material efficiency. This allows manufacturers to use the least amount of material while keeping the package safe and efficiently. By minimizing the surface area while keeping the same volume, it reduces the total material needed, and so on. It will lower the production cost since less sheet metal and plastic is used. For example, in real industry, beverage companies can optimize the bottle thickness to maintain the strength and also reduce the material cost while also reduce the plastic usage. Secondly, the importance in packaging is space utilization. It can maximize the internal space of the container so product can fit securely without any unnecessary empty gaps. This allows more items to fit in the container, and also companies can lower the shipping volume and also cut the transportation costs. For example, companies like e-commerce business rely heavily on this to cut the delivery volume and avoid wasted space too. Furthermore, the importance in packaging is it can improve the logistics and handling by ensuring the packaging has the best shape and dimension that makes the stacking, storing, and moving more easier. For instance, this can allow workers to load the trucks faster, and the automated system warehouse can move smoothly. Other than that, it also reduces the labor time and improves safety and lowers the number of transport trips needed. This will also lower the usage of fuel and also improve the environmental. Lastly, the importance in packaging is it can enhance product protection. This can ensure the packaging protects it well and keeping the cost low. It also helps protect the features such as cushioning thickness or structural strength. For instance, electronic packaging uses optimized foam thickness to absorb shock with minimum extra cost.
Now I will talk about the importance in manufacturing cost control. First and foremost, the major importance is to reduce total material cost. By finding the most efficient dimension, manufacturers are able to avoid using extra material, especially expensive parts like the iron 8 over meter square base. This will directly lower the production costs. Other than that, the another important is to prevent unnecessary design choices. This is because without optimization, a container might meet the required volume but use a larger base or higher wall than needed, which will lead to a higher cost. In addition, balance cost between expensive and cheap material. Since the base material is more costly than the side, optimization helps to determine the right base area and height. Thus, the total cost will be minimized. This balance keeps production cost low while maintaining the container function. Last but not least, support smarter budgeting and resources allocation. Companies can predict the minimum cost needed and plan their budget more accurately, avoiding overspending on material. Moreover, lower production costs also mean more efficient use of raw material, which is highly beneficial in logistics, packaging, and large-scale industrial application. That's all from us. Thank you.